Today we will first start with quality factors. Quality factor of a sensor. So it is basically defined as F0 by delta F, where F0 is the resonant frequency and delta F is the bandwidth or it is also known as FWHM, where FWHM stands for full width at half maximum. Okay, I think you have already what is the full width of maximum is. It is also known as beta in some cases. So in the case of sensors, this quality factor is very important. Keyword. Right. Because higher is the quality factor, high Q value implies that the sensitivity is also very high. S is the sensitivity. So graphically, how I can explain it? Graphically, suppose you have a cord where you have frequency in the x-axis and you have amplitude right. So you have output for two sensors. One of the sensors is giving you output like this. One of the sensors is giving you output like this. See? Or another sensor is giving you output there are two outputs. In दोनों cases में the resonant frequency is same. That means the peak frequency this is F0. The resonant frequency for both the cases is same. What is different? Different is your delta F. So if I say this one as 1 and this one as 2, so delta F of 1 is more than delta F of 2. How do we know that? If we draw the full width half maxima, that means we need to go to half of the maximum. So this is the total. We go here. यहाँ पे जो डेल्टा F वैल्यू है, this value, delta F 2, right? और ये वाला जो वैल्यू है, this value, ये है delta F1. So this situation is satisfied. So that is why. So it implies that which one is higher, Q1 or Q2? As per this equation, Q1 higher or Q2 higher? जिसका डेल्टा एफ ज़्यादा होगा कम होगा, तो Q2 is higher. That means Q2 is more sensitive. लेकिन इसमें एक प्रॉब्लम है. प्रॉब्लम है कि higher is the Qfactor, the slower is the reading. Why do you think slower is the reading? Frequency is inversely proportional to time. Frequency means what? Frequency is basically cycles per second. So frequency is inversely proportional to time. So if delta F is smaller, so delta 2, this is smaller. That means delta T is much larger. Frequency जितना कम होगा उतना ज़्यादा टाइम लगेगा, because it is inversely proportional. So that is why the reading in the case of a very sharp sensor, बहुत sensitive to sensor, तो उसमें एक प्रॉब्लम है कि the time for the real time reading उसमें नहीं होगा, it takes a lot of time. So this is the disadvantage, limitation. Time taking. So that is why we need to have a balance. Balance has to be set. That means it needs to be have जो sensor system है, the sensor system has to be set in such a way that although we are aiming for a higher sensitivity, by higher Qfactor, लेकिन we shouldn't make it too high that the time taking takes a much longer time. इतना अच्छा अब balance कैसे करेंगे? How do we need to balance? Balance के लिए we need to have dimensions in control. Okay. Now the next part of the lecture is we will see how the dimensions have a role to play in the sensor properties. Dimension का क्या रोल है sensor properties? So we will take two examples. First example हम लोग जो लेंगे is called QCM. Right? QCM. दूसरा हम लोग एग्जाम्पल लेंगे is called MWR. Can somebody say what does QCM stands for? मैंने दिया है, I think I have given the notes. QCM stands for quartz crystal microbalance. Or MWR stands for microwave resonance. There are two different types of systems which are used in sensing devices. ठीक है, और इन दोनों केसेस में dimensions of the system have a role to play. So we'll first start with this one, QCM. QCM में basically क्या होता है? It's based upon, so basically you have an electrode, top electrode and down electrode. This is also electrode. This is also electrode. This is also only electrode. Top electrode P and this is the down. Since it is a quartz, this is the quartz. बेसिकली ऐसा ही होता है। और इसमें कौन सी प्रॉपर्टी होती है क्वार्ट्ज में? नहीं, इन टर्म्स ऑफ इलेक्ट्रिसिटी में बोलता हूँ। इट इज व्हाट? इज व्हाट? क्वार्ट्ज इज piezoelectric inductions. घड़ी में जो क्वार्ट्ज है ऐसे। तो in this case, if now, so if we are supplying some electricity, it will oscillate. So it undergoes oscillations. And that oscillations will have a frequency, right? Oscillations का एक frequency होगा। और इस केस में if we have some mass on the top of it, right? This is some additional mass. एडिशनल मास यहाँ पे अगर देते हैं तो क्या क्या चेंज होना चाहिए? What do you think will change? Does echo will change? मास में दे देते हैं तो what do you think will change? No, direction is same, but in terms of frequency, change will be delta f. Change if frequency shift है with mass there is a frequency shift. जैसे मान लो एक ऐसे कैंटिलीवर, there is one cantilever, just for the sake of understanding, एक कैंटिलीवर ऐसा है मान लो, यहाँ पे तुम लोगों ने मास अटैच कर दिया, okay, so vibrations, the frequency, delta frequency change, delta f change होगा, resonant frequency वही same रहेगा, the frequency shift will change, and the frequency shift is related to the mass change by this equation 2f0 square delta m. यहाँ पे देखो, now here the dimensions become equal. क्या क्या dimensions become equal? First of all is your area. This is actually properties of the machine. Then you will have Q stands for quartz. So what are these different parameters? We have A is the area of what? Area of the electrodes. These electrodes, right? This one and this one, top and bottom. दूसरा है, this is the shear boundaries. This is approximately 29. Around 3 grams. Okay. So here you can see the dimension as a role in the frequency. यहाँ पे ये वाला mass important है, this change in mass, area and the frequency shift. These are the three very important. अच्छा ये कहाँ पे यूज होता है? Very common application of this quartz crystal macrobalance is जो thin film deposition chambers होते हैं ना, thin film deposition chambers. मान लो तुम्हारा this is the substrate, और यहाँ पे तुम्हारा डिपोजिशन हुआ है फिल्म, and it is 200 nanometers. How do we say that 200 nanometer film has deposited? We say it by means of change in frequency. Because तब ये डेल्टा m चेंज हुआ होगा, है ना? डेल्टा m चेंज हुआ होगा. From that we can say that okay, this is the amount of mass that has been deposited on the material. We know the area, हमको area पता है, तो from that we calculate कि कितना thickness उसका हो सकता है. So this is one of the examples where the dimensions have a role. इसके साथ इसका कुछ directions भी है, in which direction your force is being given, वो मैं दूसरे क्लास में बोलूँगा. timing, you can understand that how dimensions of the sensing system has a role to play in the frequency shift and detection. So now let us go to the other one, microwave resonators. तो उन्होंने प्लस 2 में ट्यूनिंग फॉर्क का एक्सपेरिमेंट किया है. ट्यूनिंग फॉर्क, सैंडिंग वेव्स, ट्यूनिंग फॉर्क का एक्सपेरिमेंट किया है. जब इसको तुम्हें से कोई है जो गिटार, एनीवन प्लेज गिटार, हाँ, सो गिटार, ट्यूनिंग फॉर्क, सब चीज़ में what you are doing is you are finding the wave, है ना? ऐसे करके you are finding the wave. इसको हम बोलते हैं ट्रैपिंग. ट्रैप. तो यहाँ पर बेसिकली हम लोग साउंड वेव्स या प्रेशर वेव्स के बारे में बात नहीं कर रहे. वी आर टॉकिंग अबाउट इलेक्ट्रोमैग्नेटिक. Electromagnetic waves, or rather I should say wave guides. We somehow trap the wave and then we use it for different applications. Okay. Now let us try to explain what actually happens. MWR, microwave, 300 megahertz से 300 megahertz, ये इसका रेंज है. माइक्रोवेव रेजोनेटर में रेजोनेटर और कोई भी फ्रीक्वेंसी रेजोनेटर में तो ट्रैप कर रहे हैं, दैट मीन्स द डायमेंशन ऑफ द रेजोनेटर इज इक्वल टू m lambda. ये बेसिकली होता है व्हेन वी आर यूजिंग समथिंग कॉल्ड कोएक्सियल वेव. कोएक्सियल यहाँ पे, so this is an electromagnetic wave, EM wave, right? Now होता क्या है कि there are different अच्छा, so डायमेंशंस की अगर हम बात करें, डायमेंशंस नॉर्मल है लेंथ, ब्रेड्थ एंड डेप्थ. ABT, length, breadth and depth. Now the waves have been trapped, standing waves. So since it is an electromagnetic wave, यहाँ पे there will be an electric component and there will be a magnetic component. दोनों यहाँ पे ट्रैप होंगे, ठीक है. तो जो इलेक्ट्रिक कंपोनेंट ट्रैप होगा, call that electric component as TE. T stands for transverse electric. T stands for transverse. So एक होता है TE, ठीक है, दूसरा होता है TM, ट्रांसवर्स इलेक्ट्रिक,
ट्रांसवर्स मैग्नेट। तो ट्रांसवर्स वर्ड से यहाँ पे मतलब है कि द डायरेक्शन ऑफ प्रोपगेशन में देयर इज नो इलेक्ट्रिक फील्ड, सो इट मीन्स दैट
so it implies the direction of propagation. यहाँ पे either there is no E or there is no H.
either there is no E or there is no H. If there is no E, it's called transverse electric, and if there is no M, it's called transverse magnetic. क्लियर है यहाँ तक? अच्छा, ना ये जो मैंने
शेप ऐसे ड्रॉ किया है ना,
this shape can be either
cylindrical or it can be rectangular.
ठीक है? अच्छा, कार्टेशियन कोऑर्डिनेट सिस्टम्स, यू नो व्हाट आर कार्टेशियन कोऑर्डिनेट सिस्टम? x, y, z.
So there is a cylindrical, it will be x, y and z. और अगर
सिलेंड्रिकल है तो फिर क्या होगा? आठ थीटा
और सॉरी 8 थीटा से
आर को क्या बोलते हैं? आर इज द रेडियल कंपोनेंट. व्हाट इज फाई कॉल्ड? एजीमुथल कंपोनेंट. और व्हाट इज जेड कॉल्ड? एक्सियल.
यहाँ पे R is radial, phi is azimuthal, बिकॉज आर थीटा दो के वेरिएशन से एक सिलेंडर बनेगा. सिलेंडर कैसे बनता है? This one, this is phi, this is z, and this is rho.
ठीक है? So it is moving in this direction, radial, azimuthal, घूम रहा है, and axial ऐसे बढ़ ऐसा ऐसा. So it becomes
Now, जो दूसरा important aspect है is
इस केस में. अच्छा,
तो अच्छा इसमें बात करें. दूसरा जो इम्पोर्टेंट एस्पेक्ट है वो है कि नोड्स.
स्टाइलिंग वेव्स में लोग नोट्स पर यहाँ पे जाके इट्स कमिंग बैक. सो नोट्स को रिप्रेजेंट करते हैं 3
नंबर्स n, n, p.
n and p, यूजुअली 0 and 1 इनका वैल्यू होता है. तो मैं अगर ये मेंशन करूँ कि
By transverse electric, if I write P as having a mode 1, 0, 1 in rectangular.
इसका मतलब है
I'm talking about F. इसका मतलब है I have one variation in the x-axis, no variation in the y-axis, and one variation in the z-axis. ठीक है? उसी तरह से मैं अगर लिखूँ T m 0, 1, 0.
That means I have only variation in the axis. And now the question is this coaxial cable. Coaxial cable में so basically there are two axes. यहाँ पे instead of having only a transverse electric or only a transverse magnetic, यहाँ पे जो होता है वो है TM, both. Transverse electromagnetic wave. Okay. So now before going into the details of transverse electromagnetic wave, Maxwell's electromagnetic equations तुम लोगों को याद है? एक बार इसको रिकैप कर लेते हैं.
क्या 4 है? 1, एक है डॉट प्रोडक्ट से रिलेटेड डेल डॉट ई, दो है क्रॉस प्रोडक्ट से रिलेटेड क्रॉस ई, ठीक है. ये तो 4 है. पहला वाला क्या है? गॉसेस लॉ ऑफ इलेक्ट्रिसिटी. चार्ज डेंसिटी. दूसरा क्या है? मैग्नेटिक मोनोपोल्स डू नॉट एग्जिस्ट, प्रोसेस कॉल्ड मैग्नेटिज्म. तीसरा क्या है? फैराडेज लॉ, ऑसिलेटिंग मैग्नेटिक फील्ड प्रोड्यूसेस इलेक्ट्रिक फील्ड. चौथा क्या है? कंडक्शन, कंडक्टिंग ठीक है. ये 4 लॉ. ठीक है. नेक्स्ट वीडियो. अच्छा, अभी हम बात कर रहे हैं कोएक्सियल केबल्स. हमारे पास both transverse electric plus transverse magnetic. That means transverse electromagnetic स्टैंडिंग वेव्स मौजूद. तो इट विल लुक कैसे दिखेगा? द लाइन्स ऑफ फोर्स, इलेक्ट्रिक फील्ड goes in the straight direction, magnetic field in the opposite direction. So it will look something like this. So this is the coaxial cable. ठीक है. So and this is center अगर ऐसा है मान लो इसको. Magnetic lines of force will be like electric field lines, transverse electric field भी radiated nature है. ठीक है. Right, radial from the center. और transverse magnetic कैसा होगा? तो यहाँ पे द डायमेंशंस का भी एक सर्टेन एस्पेक्ट है, बिकॉज हियर द फ्रीक्वेंसी और द रेजोनेंट फ्रीक्वेंसी एफ एम एन पी इज इक्वल टू सी बाई 2 over n by a square plus n by b whole square plus n by c
now just give me an answer. Inside this coaxial cable, sorry. As I give you an example, give you an answer. Inside this coaxial cable, what will be the value of delta T? Delta T का value क्या होगा? Will it satisfy delta T rho by epsilon 0? कोई चार्ज है यहाँ पे? Accumulation of charge है? So it will be zero because it is coaxial cable. There is no. What will be this one? ये तो universal है. So this will be correct. ये भी correct होगा और ये भी correct. So both will be satisfied. ठीक है? अच्छा और एक चीज़ है ट्रांसवर्स इलेक्ट्रिक एंड ट्रांसवर्स मैग्नेटिक में there is a cut-off frequency FC exists in TB and TM, but no cut-off in coaxial system में कोई DM नहीं है. इस वाले केस में if you have one enclosed, one L quadrant, one of the end is quadrant, another is closed, then you have half the field length. That means N is equal to 1. Then you have lambda by 4 plus lambda by 4. So here this is the coaxial cable length. Okay. So let us summarize what we have studied. We started with this Qfactor quality factor. Quality factor is equal to the resonant frequency divided by the bandwidth of the full width of maximum. So we gave an example of two cases where one of the case the bandwidth is much shorter
In another case, the bandwidth is much larger. So they have this opposite Qfactors. So the higher is the Qfactor, the more sensitive your sensor is. But there is a limitation because frequency is inversely proportional to time. So a higher Qfactor may cause a sharper detection, but it is time dependent. So we need to create a balance between the sharpness and the time required. The balance will come once we play with the dimensions of the sensor. The dimension of the sensor can be, there are two ways, there are two examples which have been discussed where we can play with the dimension of the sensor. One is the quartz crystal microbalance. Another one is the microwave resonator. In the quartz crystal microbalance, as you know, quartz is a piezoelectric material, and if we have a system where we have two electrodes, so the position of a foreign material on one of the electrodes, it leads to a change in frequency, which is again related to the change in mass. And here you can see that it is related to the dimensions and also the type of material we are using as a resonating system. This is one of the examples. And the next example is the microwave resonator. Resonator is something which traps frequency, traps waves. So here we are trapping an electromagnetic wave which has got frequency range in this fashion, and this is the dimension of the coaxial cable if we are using it. So we are trapping the wave. So the trap of electromagnetic waves, it comes in two different forms. One is when we are trapping the electric part of it, that is called transverse electric. Another one is called the magnetic part of it, that is called transverse magnetic. Transverse means the direction of propagation has not electric field, then it is called TE, and if there is no magnetic field, it is called TM. Then we have three different nodes related to the standing waves, and these nodes are again related to the what type of cable we are using. It can be a cylindrical, where it depends upon the axial, radial and azimuthal dimensions, and it can be rectangular exponent dimensions. So again we can have different dimensions like 101 means x, y, z, and correspondingly the radial, azimuthal and axial. And if we shorten the cable in one side, the wavelength is lambda by 4, and if it's shortened in the two sides, it becomes lambda by 2. These are the standing waves. Next, this is how the waves inside the coaxial cable look like. These are the radial transverse electric field, radial part of the center, and next these blue lines are the transverse magnetic field, which come in circular path, and this is the standard resonant frequency expression for the coaxial waves, which is dependent upon the modes 0 and 1 and kilovolts. और ये जो डायमेंशन है, लेंथ, ब्रेथ एंड ये मैक्सवेल्स इक्वेशंस सब हर जगह पे फॉलो होता है. These things remain the same. Only thing this one changes because there is no charge density inside the equation. ठीक है? Okay, so that's it for today. What are the applications? There are a lot of applications. सबसे पहले तो एंटेना. Antenna microwave. Then you have basically information. Microwave से तो मोबाइल फोन टावर्स वगैरह, फोन्स वगैरह सब माइक्रोवेव के थ्रू. और एक ऑसिलेशंस है, सेंसिंग में भी इसका एप्लीकेशन है. सेंसिंग इन दैट सेंस कि इट इज डिटेक्टिंग, आई मीन दूर से कहीं से वेव आ रहा है, सो इट इज एबल टू डिटेक्ट, प्रोपगेटिंग एंड डिटेक्टिंग.
तो वो दोनों नहीं आए, सूरज उराव और अनुराग लाखा। वो लोग आए थे, मैंने तो बोल दिया था जाने के लिए। सोनिका कुमारी एब्सेंट, लक्ष्य जायसवाल, अचिंत्य कुमार पाठक, तानिया भाटी, सुरेश भरत, सुब्रमण्यम, शुभम प्रसाद, दीपांकर कुमार, राहुल पटेल, वो अच्छा इफ्तिकार आलम, हाँ ठीक है, राहुल पटेल भी प्रेजेंट, सूरज उराव एब्सेंट, मोहन सुंदरम की एब्सेंट, विशाल कुमार, अंकुश रतन, ऋषिकेश ओझा, दीप समादार,